Hey, I'm Paul. I'm doing different things like doing hardware. So I'm a device maker for IoT, but I'm also owning a blog, an IoT blog, which the name is disk91.com. So it's disk91.com. You can get a lot of content about IoT. And so I have a strong experience in IoT area, mostly in Sigfox and LoraWAN domain. And today I'm going to talk about the Sigfox modulation. And for that, I'm going to use two of the devices I'm building. There is at first this device, which is a Fox tracker device. It's an asset tracker. And what is really interesting in my point of view in that device is that it is able to support Sigfox and LoraWAN in a single solution, in a single firmware, and basically it's the first one to be able to do that. So if I'm able to do that, it's also because I'm using a module, which is a Murata CMW1ZZABZ module. This module is based on a Semtech transceiver and STM32 MCU. So this solution is supported for both Sigfox and LoraWAN. And so in this device, you see that we have only one interesting module, which is this Murata CMW1ZZABZ that made all this modulation, but also all the functional stuff for the tracker. So after we have a GPS and some sensor like accelerometer and so on, but it allows to have a really compact solution and also a low-cost solution thanks to the reduced number of components. So with that device, I will show you how works the Sigfox modulation in terms of power consumption. We are going to analyze this using the OTI tool suite. As I'm doing another device which is also really interesting, it's the first Sigfox asset tracker based on the ultra low cost technologies, which means that this piece of hardware like this, I mean, out of the factory, cost a couple of dollars, so it's really low cost solution. It can go down to $1, and so it's really interesting and point of view for reaching the IoT at scale to be able to deploy millions of sensors and trackers. With such technology, you can do it because it's really a lot expensive. So we're going to see the difference in terms of Sigfox modulation, because if we want to be really low cost, you see that we have one constraint, which is to use a silicon battery, and silicon battery are really not expensive, that's good, but they are not able to deliver the power we need to do a transmission, a normal transmission like we have in a such device. So we're gonna see that in that video, and then we're gonna have another video where I will detail some interesting things on this device on how to select the right silicon battery for this kind of IoT. Okay, so here you see my setting with the OTI tool. I'm going to record what is happening in terms of current on the Fox tracker device, so a normal standard Sigfox device, to explain you how it works basically. So on this setting, you see that on top window I have the current consumption. On the middle one you can see the voltage out of the ARC system, and on the bottom one you can see the console, the serial console, where I can see log. I won't use it today, but that's a really interesting feature. On the right side, you have another tool, which is a SDR, so you will be able to see what is happening over the air in parallel of what is happening at the battery level. Okay, so the device is booting, and soon we're gonna have the first Sigfox transmission. You may know that the Sigfox transmission is three communications. There's 3 frames transmitted. It's 3 times the same frame that is transmitting with a slightly different encoding, but the same number of bits is transmitting. That way, we are quite sure that the message will be received thanks to this repetition and this different encoding. So after the transmission, we had a wait period where we go low power, and then we have a reception window, because this transmission is a transmission with an acknowledgement, so it accepts a downlink as a response, and as we had a downlink, you see that there is a confirmation of reception sent, and then I also have another uplink, so that's my choice to have this second uplink, for confirming, in a functional point of view, the reception of the order that is being sent through the downlink. And then there is another transmission that is starting. So it's basically the boot up of the device, which is a different message exchange between the device and the backend. So now let's look in detail what has been happened during the Sigfox transmission. So the first one including a downlink. Okay, so we can zoom on that one to have a better view of it. So you clearly see that there is 3 steps, which are the C transmission. We can see that the first transmission duration is something about 2 seconds. Okay, and this is because we have a 12 byte payload. Okay, so it's the largest Sigfox RAN we can send. So it's about 2 seconds. Between each of the transmission, between each of the repeats, we have a half a second pause, okay? And then we have the first repeat and then the second repeat. So first transmission, first repeat and second repeat have the same duration. As I said, they are the same payload with a different encoding. So the full transmission is about 8 seconds. Here you can also see the energy that is consumed for such transmission is 324 microwatt per hour that has been consumed for this. Okay, and as I said, this is a downlink transmission with a hack, so we are expecting a response from the backend. So we have a short waiting period. It's about 10 seconds. During this period, it's the time for Sigfox backend to receive the data, send it to the customer backend, and get the response to be transmitted to the device. And then we are starting a reception period. So you see that it can be up to 30 seconds. Here it has been only 12 seconds because I received the downlink at this time, and then there is a OOB transmission, out-of-band transmission, which is part of the Sigfox protocol as a confirmation of downlink reception. So the full transmission of the Sigfox with a response and an acknowledgement is 38 seconds total, and a total consumption of 700 microwatts for making all of that stuff. Sure, it depends of the time for getting the downlink. Then I have a normal uplink transmission, so that's my choice to have another confirmation of reception of this downlink. So I send a short frame. This is what is shorter. You see it's about 1 second. It's because here we have a 4 byte payload only, so it's shorter, but we still have the 2 repeats after the initial transmission, so we still have this. There is nothing else after, because this is a normal uplink, so there's no reason to have a reception or anything like this, and you imagine that the power consumption is basically shorter. Okay, here is another transmission, an uplink, which have a 12 byte payload, so it's back to the 2 seconds and so on. So now, as we have seen this part, we're going to compare it with the ultra low cost design, where if we want to use silicon battery, we can have this kind of profile of consumption because it's going to be too high. So it's different, and we are going to compare this with the second capture, where basically I reused the initial capture and I had a second measure, so we are going to be able to see the both capture each on top of the other, so it's going to be easy to compare it and see the difference. So here you see that the level of the current is really lower. You can also expect the duration to be a bit smaller also. And for getting more detail, we are going to align the different measurements, and so that will be really more easy to see. So here you see I can select the shift I want to do, and then ask to move the graph from to the right here. So they now are aligned, so it's really more easy to make a comparison. And as you can see, there is a big difference in terms of current consumption. So that means we are going to preserve the battery by such modulation, and also the duration is really shorter, as basically the ultra low cost solution is only transmitting 1 bit frame. No, not byte, it's 1 bit frame. So that's why it's quite shorter. And so we can also compare the power consumption of these two things. You see that in terms of energy, we have a big difference, as the ultra low power is 87 microwatts per hour when the standard uplink was 300. So we are far lower, and thanks to that we are able to use CR2032 batteries, which are really low cost and match with what we are looking for. And now in the second video you are going to see how I'm being able to select my battery to get the best benefit between battery performance and price.